Dr. Narsinga, Professor of Physics, Dean Research and Development, Marri Reddy Institute of Technology and Management. So today we will discuss about nanoparticle preparation. So how we can prepare the nanoparticles. So there is a two different type of approaches to make nanoparticles. So those approaches are like a top-down method. One is a top-down method. Another one is a bottom-up method. So usually top-down means like a bulk material. If you crush that one, it will make as a powder. That way we will make nanoparticles. That is call it as a top-down method. That means initially it will be bulk material. Then it will becomes nano size. Go on decreasing the size, it will be like nanoparticle. So like one statue, if you take a big rock, then if you want to make a statue, it will be smaller size compared to earlier one. Similarly, this nanoparticle also, if you make the bulk material to crush that one, it will make a nano size. So there is a different type of methods will be there in that top-down method also. Okay. So the top-down method, it is nothing but cut away from the material. So that means we have to slowly decreasing the size. Then we will get the required nanoparticle. So it depends on the method, how we can cut it down, we will see that one. Okay. So that is a top-down method. Another one is bottom-up method. This bottom-up method is nothing but it will be like a solution. It will be like a liquid. Then it will from liquid to nano size. That's a particle will come. Liquid to particle will come. That is called it as a bottom up. Initially it will be like a liquid, then it will go like a nanoparticle. So that we call it as a bottom up method. So it's nothing but assembling it from a building blocks such as atoms. One by one atom it will be attached. Then it will call it as a bottom up method. So it's atom by atom molecules or molecules are cluster. So using this type of method, that we call it as a bottom up method. So how we can these two type of methods, how it will be. Okay, we can see here there is a top down approach. It will be slicing the successive cutting of bulk material to get a nano sized particles. So just this diagram tells that there's a bulk material. If it's like a rock type, then we will crush that one. So there should be some powder, that is we call it as a polycrystalline powder. So then if you go on crushing that one, so you will get the nanoparticles. These red ones are nanoparticles. It will be depends on the material how the nanoparticle will be behaves, as well as how we can prepare these nanoparticles. So there's a similar type of, what I mean is, if the material, one type of material, okay, let us take it as some copper oxide. If you want to make a nanoparticle of this copper oxide, so is it possible to make in a both way, top down or bottom up? Yes, it will be possible in both ways. Some materials we cannot make in both type of methods, approaches. What I mean is top down and bottom up. There will be limitations for those materials. So that is top down approach. That means bulk to nano. So initially it will be big size, then we reduce to nano size. That we call it as a top down method. Similarly, there is a bottom up approach. That is bottom up approach is nothing but slicing of this one is not. Okay, 1 minute. So there's a attachment of the atoms, attachment of atoms or molecules. That means if you are molecule, these atoms, so that means it will be in a liquid form or some type of things will be there. Then there will be clusters will form. That means 2 or 3 together it will be formed like a cluster. Then once again it becomes nanoparticles. So this is a bottom up approach. Earlier one it is top down approach. This one is bottom up approach. So how these approaches will be useful for making the nanoparticles, we will study now. And in these two processes, that is the two approaches, bottom up and top down approaches, there is a different type of methods. So I just note down a limited number of preparation methods, these making nanomaterials. So that synthesis techniques, there is a top-down approach. There is a top-down approach. There is a lot of different type of methods will be there. So that is first one. There is a ball milling. So this ball milling is nothing but in earlier days, everyone will watch like rice and rice flour. So rice means bulk one. Rice flour is smaller size. It may not be nano, but it will be in a micro size. So if you go on decreasing the size, that means go on grinding that powders, then you will get the nano size of that material. So that is call it as a ball milling. Ball milling is nothing but is rotating in a two. There is a two different strong bodies. From strong bodies, in between the powder will go, then it will be crushing that one, then you will get the nano size. That is a ball milling method. That is also call it as a top down approach. And one more terminology, it will we call it as a physical methods. That means we have to work on that. That machine should work on that. That is call it as a physical methods or top down approach. It will be same, physical as well as top down approach. So there is a ball milling is one type of method where we can make nanoparticles. Similarly, there is a thermal evaporation. This is also physical method only. If the heat of that material, if you keep some furnace or some zone, that is a evacuated zone, so then if you make that bulk material, then if you evaporate that material, then the fumes will be coming and there will be formation of particles will become. So that type of method, they call it as a thermal evaporation. Thermal evaporation also we can use from bulk to nano. These all methods are using raw material is bulk, then final material is nanoparticles. So that means the top down approach is ball milling, thermal evaporation and laser ablation. Laser ablation also one type of evaporation only, but there is a, instead of thermal they will keep light, then the material will be evaporated. That means the fumes will be evaporated from that bulk material, then it will be coated in some lower intensity area or lower temperature area, then you can take out those nanoparticles. That is also labor ablation, they call it as. The another one is sputtering. This is also, these all methods are from bulk only. Sputtering is nothing but if they use bulk material, a 2-inch pellet or like that, they will make a bulk material. Then they will heat up this material. Then there will be plasma will be created. The plasma, that is a different type of physical method. It requires a lot of instruments to see that evacuated, how much evacuation it will be. So how much gas is inside. That they use because if you use this sputtering method, it will be, if there is outside, there will be oxidation will come out. So they control the oxidation. You have to keep some type of gases, that is helium or neon. These are the what we call it as a helium, neon and argon. So these gases, it won't react with oxygen. So that's why they use this type of gases in that chamber. So then there will be electric means discharge tube, that's it will be heat up using that electrical power. So then there will be evaporation of this pellet from above this point. Then that fumes will be coated in that above temperature range. That is temperature will be less, means it will be coated in that place. So that material we can scratch out and we can take it as a material that if you check that one, it will be nano size. So that's depends on this material. The size of the particle also depends. So usually if it's a gold or silver, so you can easily make 1 or 2 nanometer particles. 1 or 2 nanometer particles. If there is a oxide one, so it will be very difficult to control the particle size less than 5 nanometers. So pure metals, it will be easy, but if you want to make the oxides, it will be difficult to make below 5 nanometers. So it requires some more extra work we have to make. So that is physical methods. Similarly, there is a bottom-up approach. That bottom-up approach is nothing but chemical methods. It call it as a chemical methods. Okay. So first one is physical method, another one is chemical method. This mostly they use like chemicals here. So that is bottom-up approach. That is the molecules, they will attach together like a cluster, then cluster to nanoparticle. So here the process you can see here, there is a atoms are attaching together like a cluster, then nanoparticles. Similarly, you can see in a top-down approach, the bulk one is crushed to powders, then powder to nanopowders or nanoparticles. So that's a process of making this top-down approach. This one is bottom-up approach. In bottom-up approach, from atoms to nanoparticle. That means nanoparticle is nothing but combination of few atoms. That's a trend, it will be nanoparticle. So in this bottom-up approach, there is a chemical vapor deposition. Chemical vapor deposition. Here in chemical vapor deposition, they use one or two chemicals, extra chemicals. In ball milling, they won't use any extra chemical. They use only bulk material. Whatever you want to make that nanoparticle, if you want to make silver nanoparticle, they use silver only to make a 2.5 inch like that in this method. So in ball milling, the silver powder they use, then they will grind with a different type of means balls, like ball milling is nothing but balls using milling. There is a different type of balls will be there. We in the children's, they will means play with silicon balls. In our childhood, we used to play that mm, balls also they use for grinding, like a ball milling method. So that is one advantage of this ball milling, to make a large type of particles also. Means the amount will be large in some of the methods. Okay. Similarly, in a bottom up, it will be chemical method. So when the atoms will be together attached, then there will be cluster will form. From that cluster, we use to make a nanoparticle. That's a process of this bottom up approach. Here, there is a chemical vapor deposition. So here, the physical vapor and chemical, the thermal evaporation, that nothing but physical vapor deposition. So the chemical vapor deposition and physical vapor deposition is nothing but, if the chemicals they use, the liquid they use, then it will be evaporated, or they use like two different solutions. From these solutions, they use in the furnace, that's some temperature one. So then it will be evaporate. This will be evaporated using these temperatures. So then they will be material will be forming in a lower temperature side. Then it will be scratch this metal plate or some type of substrate. Then you will get the nanoparticles. That is a CVD method, chemical vapor deposition. So second one is, another one is hydrothermal. Hydrothermal is nothing but they use different type of liquids, like if you want what I mean is copper oxide. I will use copper oxide nanoparticle if you want to make. So for that purpose, what you have to do is copper acetate, some chemical compound you have to take. Then there is some other acetate, you want to remove that acetate, they use another chemical, A plus B. Mix it together, then there will be big means iron cylinders will be there, like these cylinders. So there is a evacuated, there's closing will be very means tight closing will be there. That screws also it will be there. So there they will use the material here, the liquid, this A plus B, that is acetate and some other material. They use inside the box, they close this one. Then it will be applied in a temperature. So that means here they will apply some pressure. Then there is a temperature furnace they kept like that. So this material, it will be in a pressure mode. So that means it will be applied some pressure. Because of that, it will be, and a temperature also there. So because of that, the reaction takes place, then the nanoparticles will be forming in this way. So that method, they call it as a hydrothermal method. That means the liquid in temperature range as well as pressure. So this method, they make nanoparticles. Means all nanoparticles, not necessary to use all the methods. So some is easy to make in a sol gel also. Most of the nanoparticles you can make sol gel. Why hydrothermal? Why CVD? So sol gel method has some disadvantages. Similarly, CVD has some advantages. So then they will together they will match. Then which one is better? They decide. Then they will make the nanoparticles, required nanoparticles with accurate particle sizes. So some of the methods we cannot make accuracy, but some methods we can make accurate particle size. If you want 2 nanoparticles, 2 nanometer size particles, so there is a method to make the 2 nanometer particles also. But 2 nanometer for all materials we cannot make. Only few type of materials only we can use that type of method. So similarly, co-precipitation. Hydrothermal is some pressure and temperature. This co-precipitation, the meaning itself here. If you make like, if you want to make our homes, if you want to make that milk to, what we call it, I say, if you want to spoil this milk, what you have to do? You just one pinch of lemon, it will be enough to destroy this milk. Then it will be transferred to another material. That's a different story. But here that will be like that. So co-precipitation also similar. Co-precipitation means they have some salts. So from that salts, like if you want to make a co-precipitation, that's the best example is iron oxide nanoparticles. Best example is iron oxide nanoparticles. For that purpose, they use FeCl2 plus FeCl3. Okay, so they mix together in a water. That means deionized water. There will be no extra impurities will be there in that water. So then they will use some base. Base means NaOH is a base material, or ammonia, that is also base. Okay, so these type of base they mix together. That means this is a salt solution. This is salt solution plus base solution. So they just keep in a one like a what with the flask, then just keep drop wise with burette. You know the burette, most of the people they know burette. So there is a, here it will be salt. It's a salt solution. Which type of material you want, you make like that. But we study this iron oxide. So for that purpose, you have to make FeCl2 and FeCl3, or you can make sulfate also, or you make nitrate also. This salt should be, it will be dissolved in a solution. That's a basic idea of this sol gel co-precipitation or sol gel method. Okay, so with this, if you just drop this one, then there is a dark particles will be formed. So with these dark particles, if you are rotating this one, so then the dark particle will be dissolved. So if you go on adding, so when the pH value also important here. So if the pH is around 7, then you will get most of this material will be black ones. So the black is nothing but is a particle of iron oxide. Here there is a directly, it will form the iron oxide nanoparticle. There will be no extra. Iron oxide, maybe some sodium nitrate will be there if you use sodium, or ammonium nitrate will be there if you use ammonia. So that's why we will directly get this iron oxide plus NaNO3. So if you dissolve that in water, so NaNO3 also go out, then you will get pure iron oxide nanoparticles, Fe3O4 nanoparticles. So this desired nanoparticle, it may not be exactly desired one, but you will get most of the nanoparticles will be range of 15 to 20 nanometers. Like that range it will be appear. It's not only all particles may not be in a same size. That's a disadvantage of this chemical methods usually. Okay, so that's iron oxide one we can make in co-precipitation method. What is the difference between co-precipitation and gel? Co-precipitation means directly it will be precipitate out, but gel it will be solution only up to certain temperature. After that it will make like a gel, like a pudding. So before pudding, the two materials will be similar, but after some time or after heating, then it will be like a gel type. That means the pudding will be formed. So similarly, sol gel method also like that. Sol gel, its meaning itself is that sol means solution, gel means it's like a dense material. So this one here also, if you want to make some type of oxide materials, I am just explaining this one. Chemical methods mostly we use um, oxide material, but some we can make silver or gold nanoparticle also we can use using these methods. So nickel oxide nanoparticles, if you want to make, if you have to take NiCl2 plus H2O plus NaOH, same. Here the what I want to say is, if what is the difference between these two? Here also there is like a precipitation, but here there is no precipitation. So here there is a formation of gel, it will form directly. This NaCl2 plus H2O, this salt solution versus base solution. So these two if you mix, then you will get the green gel. The color will be green. It's like a gel form, like a dense material. So this green gel looks to be, it's not a nickel oxide nanoparticles. It should be NiOH, hydroxide. So that means the hydroxide is formed. It's like a colloidal, like a cluster type it will form. So we are taking atoms, nickel chloride atom, NaH2 atom, NaOH atom and H2 atom. So the atoms we are mixing. So these atoms are making like a cluster, NiOH2 clusters. All will be aligned like that, NiOH2 type. So there is a cluster type. So we want to make nickel oxide. Then what you have to do is you have to heat up this NiOH2, particular temperature like 200 degrees centigrade. Okay, because if it is a 200 degrees centigrade, you will get the NiO. Then remaining water, where it will go? It will like evaporating to H2O. H2O will be evaporated. You will get the nickel oxide nanoparticles. This particle size will be some around 5 or 6 nanometers, like that. So this way we will make gel method. So gel method, I will show you some of the diagrams how the gel will be forming. So now we will study about the gel formation. And one more before going that, so there is a advantages of top down approach and bottom up approach. In advantages, there is a large scale preparation we can use like physical method or top down method. So large scale production, as well as the deposition over large substrates. So very big substrates, you can use this top down approach. Okay. So similarly, the chemical purification is not required. So here, whatever your material is taking, so the pure one only, it will be evaporated at that point. It will be grinded while grinding. So remaining extra things will be go out. So there is a special purification is not required for these top-down approaches. So while making itself, whatever the impurities are there, whatever the extra chemicals are there, that it will be going out using this top-down approach. Whereas bottom-up approach, you can use ultrafine nanoparticles, and here you can use only type of particles. Here you can use nanocells, you can make nanotubes, we can make. So these particles, tubes, cells, all these we can make through bottom-up approach. Usually this bottom-up approach, while using that chemicals itself, so we can see there will be some type of what I am, because I did research on copper oxide, so I know how it will be changes. So you can see the copper hydroxide, it will form like a sol gel method. Then if you heat up around 200 degrees centigrade, so you will see there is a particle like these structures, like what we can say, it's uh, leaves, like leaves. So that means there will be lot of atoms will be surrounded by this. But if you check this one, it will be pure copper oxide only. But the morphology, and it is forming, that cluster will be forming like a leaves, or some it will be different type of means shapes will be arranged in that lower temperature side. So if it is in between the temperature, these leaves will transfer to like tubes or wires, different type. It depends on the method how we can vary this temperature, and there is a different type of morphology it will be forming. So what they say is nanocells, nanotubes are because of this. Then if you heat up little higher temperature, so you will see the particles like circular means sphere particles will be appears. So that means depends on the thermal energy as well as inside how much, which type of chemicals you are using. Those things will be useful, means depends on this morphology of the particles. The nano, if maybe nanoparticle or nanocell or nanotube. So nanotube means its morphology is only nanotube, but in that nanotube there will be lot of nanoparticles will be there. Okay, the arrangement is like that. The morphology is like a nanotube. It's not like a single bits like copper sheet. If you take the tube, it's not like that. So here in the nano size means there will be small particles will be arranged along the is morphology, along the shape will be like a tube. So that if you little bit higher temperature, but in outside if you look from our naked eyes, it will be like a powder only. But if you see in the microscope, then only you can see it will be like leaves or tubes or particles. This tube also it will be in terms of nanometer only, not very big size of tubes what we are using like water or gas, not like that. So it will be only few nanometers, or if it is maybe maximum it will be 100 nanometers, like that size means length of this tube depends on that. So that's nanotubes we can make, as well as nanocells like nanoparticles. These can be prepared using a bottom up approach. And if you want to make thin films, so it will be controlled deposition, whereas in chemical physical vapor deposition and sputtering, so there will be no parameters we can control that deposition rates. So here in this bottom up approach we can control the parameters to deposit. And there is a size distribution is a narrow size distribution, that's 1 to 20 nanometers, but it's not like a narrow. So but its variation is more, what I told in physical methods it will be very fine particles we can use, but in chemical methods we can use the variation will be 1 to 20. So in that 1 to 20 itself, there's lot of variations will be there in properties. So that's one type of disadvantage actually. It is possible different type of this one. And this bottom up approach is cheaper. There will be no extra instruments required, especially one or two. But this it's a technique is cheaper, you can make it more nanoparticles. Whereas is top down, so it requires a lot of instrumentation to make the nanoparticles. So that's advantages of bottom up and top down approach. So next one is disadvantages. So what are the disadvantages in top down approach? So yield, in a yield there is a broad size distribution, but it's some of the methods you can see there is a 10 to 1000 nanometers. Then varied particle shapes and geometries in the top down approach as well as bottom up approach also it will be like that. That's a disadvantage. And control over deposition parameters is difficult to achieve. So we don't know when we will get the particle, when we will get the nanotube, when we will get the different type of morphology. That's the controlling deposition parameters is difficult in a top-down approach. That is a physical methods. And here in top-down, there is a impurities will be there. That impurities is like a stress, defects, imperfections. It's not like chemical impurities. It's a inside there is a material impurities. That is imperfections, defects. That is a stresses inside. That will also problem. And it will be expensive technique. The top-down approach, whatever we take the top-down approach techniques, it will be expensive. Like ball milling also, you want to make a machine, everything, it will be costly. If it is a sol gel method, if you just buy some salts and base, so it will be enough. Every chemical laboratory in lab, so we have rotators as well as the what I'm saying is pipettes and burettes, like deionized water will be available. So that will be compared to top down approach, bottom up is cheaper. And a large scale production is difficult in a chemical method, because if it is large scale, if 1 kg 2 kg, it will be difficult using these chemical methods. And chemical purification of nanoparticle is required here, because we are not making any extra efforts to make that evaporation, whatever it is. Here it requires the pure compounds is required. If you want to make some salts, sodium hydroxide, that's also pure one it required. So similarly, the metal salts also, it required the purity is important in this chemical approach. So then we will study about sol gel method, that is a bottom up approach. So the bottom up approach, the solution is a stable dispersion of particles or polymers in a solvent. The particle may be amorphous or crystalline. So it may be amorphous or crystalline. So that means amorphous means it will be no X-ray diffraction. If you take, that will be every atom to atom, there will be no arrangement of atoms. Randomly it will be arranged. So that's why we cannot see any structural parameter of that polymer. So then crystalline means we all know that there will be crystalline structures will be there. That's 7 crystal structures. With that, any crystal structure, it will be, the particle may be amorphous or crystalline. That is a solution. That is a salt solution. Similarly, gel consists of 3-dimensional continuous network. This, what I told is the gel means NaOH. So this is a continuous process. That means it's a 3-dimensional continuous network. So that means nickel will be there. One is OH, another OH. This is connected to another nickel. Like that. It is not breakable. It is a continuous one. Okay. So that continuous one, if you heat up, then it will be changing this continuity. So once the gel consists of 3-dimensional continuous network, which encloses in a liquid phase. That is a gel formation is like that. So it's a liquid form. So these all 3-dimensional arrangement. The network of NaOH OH group is continuous process. Okay, that is in the network type. So this to dissolve the compound in a liquid in order to bring back as a solid in controlled manner. So that means first we have to dissolve the salts, then we make the another type of material with the controlling like a pH, like a temperature, whatever, that is in a controlled manner we will make a solid. So enable mixing at an atomic level. So that means means the liquid means it's a atom to atom interaction that will be there. So in the results in small particles which are easily sinterable. That means easily we can make heating that material. That's a bottom up approach. That is one of the method is sol gel method. So you can see here there's actually there's a block diagram of the sol gel method. You can see here if the two there is a metal salt and a base we dissolved in a beaker. Okay, mix the reactives. Then there will be some heating process, small heating temperature. Okay, then condensation reaction takes place. So once the condensation takes place, what will happen? There is a solution and the particles. Solution and the particles will form this a solution. So then from this solution we will make a, there is a gelification. Gelification is nothing but if you just wait some time, so this solution becomes a dense one. Okay, like a milk to what we call it as a junnu or some type of other material we will make, like that it will be gelation is forming. So once gelation is forming, so then we remove that water, then it will be the aging will come. Aging means if you remove the water, then it will be one to another, it will be more dense material it will form. Then there is a drying method. Drying is if you heat up that gel, so then you will make a aerogel. So aerogel means is nothing but fluffy material, like bread. If you want to make a bread, so initially it will be solid type, but it will be like a not exactly solid, but it is a semi solid. So if you heat up that one, then the bread will form. Inside there is a lot of holes will be there, that we call it as a aerogel. So we can see here there is a one more picture. I will show you this. Like this, it's like a bread. This is a dried gel. So from this we can crush this one, then we will make another higher temperature compared to this one, then we will make the nanoparticle. So here this gel formation, aerogel is nothing but if you the Sol-Gel method, if it is NiOH, this is the gel formation, this gel NiOH tries. So if you heat up this material, then only you will get the nickel oxide. Initially it is nickel chloride or nickel nitrate, then NaOH, then mixed together, then just waiting some time, and then if it is forming the gel, okay, or solution, that one, then gelification, then if you remove the water, then aging, drying, then aerogel. So aerogel is nothing but NiOH tries. This is a continuous network. It's like one to another, it will be attached like a bread. So this is NiOH tries. Then if you heat up that material, so you will get the NaO particles. So it is actually this Sol-Gel method is developed around 1960. Why this Sol-Gel method is came into picture means there is a dust will be more in making some type of like ceramic materials using salt state reaction, like just heating that two materials, then using in a furnace with high temperatures. So that is a lot of energy waste, as well as the dust also we can reduce using this gel method. This gel method is developed in the 1960, but before that also there is some other materials it will be there, but the mostly the Sol-Gel is famous after 1960. So this is the history of the Sol-Gel method. So actual experiment, how it will be, the different stages of Sol-Gel process, how it will looks. So you can see here there is a precursor as well as solvent. That means NaOH and salts. Then the solution will be forming. This after this it will be solution form. Then there is a some colloidal structure. That means it's a gel. Gel will be one to another. It will be attached together. Then you can see after some time the water means the solution will be upper side. Then this bulk material like a gel one will be in a downside. So that gel you are taking out from supercritical, that is a drying one. So that means if you just using that filter paper also, it will be okay to eliminate that solution one. Then in that filter paper you will see there is a gel one will be there. So that one, if you use that supercritical drying, so then you will form the aerogel. That means very small amount of heating, so you will get aerogel. And directly if you dyeing also, you will get the aerogel, xerogel or aerogel. These are the just method of things. Then freeze drying. So that means same temperature, if you keep more time, then you will get the cryogel, like that. So there is a different, means eliminating that water quantity, extra water quantity. Then if you calcination of these gels, you will get the final product. Like if you use nickel oxide, if you use nickel salt, you will get the nickel oxide. If you use copper salt, you can get the copper oxide. If you use zinc oxide, you will get zinc salt, you will get the zinc oxide. Like that, the particles will be forming after calcination. Before that, it will be some type of continuous structure will be there. So that structures, it's like aerogel or xerogel or cryogel. So that means depends on the temperature actually. The cryogel means it will be lower temperature. If the freezing, like if you use at lower temperature, like freezer, if this gelation, if you use a freezer, then that will be cryogel. If it is a little higher temperature, that will be xerogel. Then there is a just evaporating that water, then it will be aerosol. So these are the three different type of aging and drying techniques. So finally, if you calcination is nothing but heating that material to higher temperature, 200 or 300, depends on the material where the water quantity will be go out. If it is a nickel oxide, it will be around 200 degrees centigrade, that water content will be going out. Whereas if you are copper oxide, it will be around 150 to 160 degrees centigrade, the water quantity will be go out. Whereas zinc oxide, it will be more than 200 degrees centigrade. So that's how we can calculate, means we have to make some thermal analysis, then we can know the where the temperature, the water quantity is going out from that circuit, from that network. So in that way, so which temperature is suitable, that temperature we will use to make nanoparticles. So this schematic diagram of the sol gel method. So this dried gel, how it looks to be. So these are the references I took from that books. Introduction to Nanotechnology by Charles and Poulet, as well as the chemistry of nanomaterials, synthesis properties and applications of applications by C.N.R. Rao is Bharat Ratna, as well as A.K. Cheetham and A. Muller. These are the England scientists. So I have used these books to refer my PPT. Thank you.